Hi guys, welcome to the next section, Docker. In this section, we will see Docker architecture and internals. We will then see building Docker images. After that, we will look at Docker registries and volumes. Finally, we will see Docker networking and compose. Now, we move on to the first video of this section that deals with Docker architecture. In this video, we're going to take a look at the architecture and concepts of Docker. We will also see Docker internals. Next, we will see Docker's client. One of my preferred ways of learning is through experimentation. In order to explain the Docker architecture, we're going to show an example, but first, we need to install Docker itself. In my case, I'm working with Ubuntu. At this link, you can find the distribution that suits your needs with a very clear set of instructions. Once you've installed Docker, run this command. We will get a message from Docker. This message shows that your installation appears to be working correctly. Let's see some newly introduced concepts. First one is Docker Hub. This is a central repository which is public and private, where users can push images that they build locally. A Docker registry is used to carry the images across different stages of the deployment pipeline. The next concept is layer. Docker images are composed of layers. A layer is basically an ordered file system difference. A Docker image is a stack of these layers leading into the final image. When you change a file in an existing image, a new layer is created, but the rest of the layers of the images are reused so we can save a lot of space. Next are the Doker Daemons. Docker follows a client-server architecture. The Doker Daemon is the server part that could be operated via a representational state transfer API. Last one is the Docker Client. Docker Client is a command-line interface, CLI, used to operate a Docker daemon. It might be a local daemon or a remote one. The last three concepts are the key for drafting the architecture of Docker. Let's take a look at the figure. The client-server architecture predominates the software. In this diagram, we can see how the Docker CLI is able to manage a local instance of the Docker daemon, but is also able to talk to a remote daemon by setting an environment variable called Docker host. One of the key points of Docker is that it completely leverages the virtualization to the Linux kernel, making it impossible to run Docker on Windows or even Mac, as it uses the capabilities of the Linux kernel. The solution to this is to create a virtual machine with Linux that runs the Docker daemon, and the CLI will talk to the virtual machine to run Docker commands. Now we move to Docker internals. Docker provides you with only a runtime for your applications. You can limit the number of cores and the amount of memory to be used by the container. By the end of the day, the kernel running your container is going to be the same as the kernel running your host machine. The proof of that is in the way Docker organizes images. It calculates files system differences and packs them in layers that can be reused. Let's pull a fairly big image. As you can see, Docker has pulled 5 layers, which basically tells us that the Ubuntu image was built in 5 steps. Now we're going to run an instance of Ubuntu. In Docker, an instance of an image is what we call a container, and the main difference between an image and a container is the top writable layer. Layers in Docker are stacked in the read-only mode to compose the image, such as the diffs in several patch files. Let's demonstrate this. This command runs /bin/bash in an instance of the Ubuntu image. The I and T flags allow you to use the container as if it were a virtual machine, allocating a virtual TTY, T flag, and creating the interactive session that is the I flag. Now we can see how our prompt has changed to something like this. It does not necessarily have to be the same, but it should be similar. Note that your prompt is now a root prompt, but don't get too excited. It is just inside the container. We will create a file to alter the file system using the touch command. Now we can disconnect from the container with the exit command. As you can see, the prompt is back to your system prompt. If we run the docker ps command, we can see that there are no running containers. But if we run docker ps-a, we'll show all the containers, not just the running ones. This is a container that has been created from an image but is not running anymore. As we said earlier, the only difference between this container and the image is the top writable layer. In order to prove this, we're going to create a new image out of the container that we ran a few minutes ago. In our case, I'm using this reference because it is the one shown in the output of docker ps-a command. In fairness, you don't need to type it all, just a few characters will do the job. If everything went well, the command should output an SHA-256 checksum and return the control to you. Now run Docker images to list the images in your Docker. The output should be similar to this. As you can see, there is a new image called My Ubuntu that we just created. Now we want to check the difference between the Ubuntu image and the My Ubuntu image. In order to do that, we need to inspect the layers for each image and see the difference. The command we're going to use to accomplish this task is docker history, with the name of the image as the third parameter. First, for the Ubuntu image. Then for My Ubuntu image. Quite illuminating. The image My Ubuntu is the same image as Ubuntu except for the top writable layer that we just created by logging into the machine and creating a file. This is very smart because even though both of the two images use around 130 megabytes of space, the only extra space used for the second image is the top layer that, in our case, uses only 20 bytes, leading to a usage of 130 megabytes and 20 bytes for the two images. A container is the exact same thing as an image, but with a different top writable layer, so running an instance of the container uses only 20 bytes of space. As you can see, the engineers that created Docker thought about everything. The way in which how Docker stores the images in the hard drive is the responsibility of the storage driver. Docker can make use of different drivers and store the images in different ways. The default driver stores the images on the hard drive, creating one file per layer with the checksum of the layer as the name of the file. Now, let's see Docker Client. If you have dug into Docker a bit before, you can see that the commands are quite verbose and not as intuitive as you might think. The most common use case is using this combination. This command basically does one simple thing. It runs a container in the interactive mode and allocates sudo tty. This allows us to interact with the container executing the commands. Let's see what that means. The command should return a prompt similar to this one. What just happened? The prompt changed to root with a strange number in the host section. We are in the container. Basically, now we can run commands that are going to be run within the container. To exit the container, just type exit and the control should be returned in the terminal to your host machine, leaving the container running in the background. Imagine that you spin up a Jenkins server and you don't want to have your terminal attached to it. In order to do that, we just need to add the -d option and drop -i and -t. Once the image is pulled and it starts running, the control is returned to terminal. The last line in the output, and it should be a long string of characters. This is the hash of the running container. If we execute docker ps, this output will be produced. Note that the value under container ID matches the first few digits of the hash. Now in theory, we have a running instance of Jenkins that. As you can see, it is listening on port 8080 and port 50,000. Let's try to browse localhost 8080 with an internet browser. Nothing. Basically, our browser cannot open that URL. This is because we haven't told to Docker to bind the container ports to the local ports of the host machine. In order to do that, we need to first stop container and then start it again with a special parameter. It's time to learn how to stop containers. We have two options here. The first option is stop the container. With the stop option, we send sig term to the main process within the container and wait for it to finish. Then we send sig kill. The second option is kill the container. With the kill option, we send sig kill to the main process in the container, which forces an immediate exit without being able to save the state. In this case, which one you choose is irrelevant, but please be careful. When you're running in a production environment, make sure it's fine to kill a container. Before doing that, as with the stop option, we're giving the running software the option to save the current transactions and exit gracefully. In our case, I'm going to kill the container using Docker kill command. Docker is smart. I did not need to specify the full container identifier. With only a few characters, Docker is able to identify the container and kill it. When we killed a container previously, we have a layer left that leads into a dead container that we can explore by adding the -a option to the docker ps command. In this example, we're going to remove the layer using docker rm command. That's it. The container never existed in our host. Now, going back to the Jenkins example, we want to run Jenkins in a way that we can access the running instance from our browser. Let's modify our command and run it. After a few seconds, if we go to localhost 8080 in a browser, we should see the initial configuration for Jenkins. It will ask you for the initial password to be able to proceed. Let's explain the command first. We can see a new option here, that is -p. As you can guess, -p comes from the port. In fairness, you could change -p for --port, and everything will work as expected. With the -p option, we map ports from the host, your machine, to the container. In this case, we're mapping port 8081 from the host to port 8080, and port 50001 of the host port to 50,000 of the container. But how can we map a different port in the host? Well, it's fairly simple. After running this command, we have two instances of Jenkins running. The first one is exposed in port 8080 of your machine. The second one is exposed in port 8081 of your machine. Note that even though we don't use port 50,000, I've changed it to 50,001. As our machine's port 50,000 is already busy with the first instance of Jenkins that we ran earlier on. As you can see, Jenkins is asking for a password, and the initial web page in localhost 8080 states that this password is in the logs or in the file system. Focusing on the logs with Docker, we can fetch the logs for any container registered by the daemon at any time. Let's try it using the docker logs command. In my case, the running instance of Jenkins on port 8080 has an ID that starts with 76561. Another interesting and common option in Docker is passing environment variables to an application running inside the container. If you think about it, there are only three ways in which we can configure an application within a Docker container. The first way is environment variables. The second way is volume with data. And the last way is fetching the configuration from the network. Let's take a look at the official MySQL image from the Docker Hub at this link. MySQL is a popular database server that has also been Dockerized. If you read a bit through the documentation, one of the config options is the root password for the MySQL database. In fairness, the Quick Start example points to the right direction. The new option here is -e. This option allows you to pass an environment variable to the container with the value that you want to specify after equals to. Next, we're going to run the docker inspect command. In this case, the ID is that results from running MySQL on my machine. There should be a huge JSON output in the terminal, but one section in particular, config, has a subsection called env. There it is. The environment variable that we passed, MySQL root password, is now accessible from within the container as the environment variable. In the Docker inspect command, there is a lot of very valuable information. The best way to check what is going on is through the documentation on this website. There is also a reference of the commands of your current Docker installation available under the Docker help command. In this video, we've looked at Docker architecture,